viewers, welcome to CEC lectures. Myself Dr. Preeti Jagmani from Department of Computer Science, Aryabhatta College, University of Delhi. So as you all are aware that presently we are studying the series of operating system concepts, and in our couple of previous lectures we have basically seen that what actually the operating system is and how it why it is mandatory and what is the level of interaction it is going to take with the hardware as well as with the users. Continuing with the series, today's agenda is the structure of operating system. So basically that the fact which we have already witnessed, that it provides basically the operating system, it is a kind of system software which provides the environment for program execution. Now when we say environment for program execution, this is kind of, I can say it's a vast term or it is a huge term, and because of this responsibility being very huge which is entrusted upon the operating system, it has many different components, and each and every component is having its own way of doing executing the task, and each and every component is having its different own assigned task. So overall these components together are going to provide us or are going to provide the computer system and environment for program execution. So basically when we talk about various components, so we can say that there is going to be something which is very common or something which is kind of common in all the operating systems, be it kind of type 1 or be it kind of type 2 or whatever. But along with that commonality, there comes a variety also, because the way it is going to execute the things. So for example, we have kind of variety of systems, as in we can say we have multitasking systems, we have single tasking system, we have multi-programming systems. So depending upon those systems and depending upon those tasks, there is going to be variety of the variety in the structure of operating system, but ultimately it has to provide the environment for the execution of program, and because of this common reason it is also having some commonality. So we will be exploring various operating systems, and we can say there is variety along with the commonality also. Now when we say a particular program, so as you all are aware that one of the major agenda or one of the major task of the operating system is to keep the CPU busy for all the times, because CPU is actually not only CPU but input output devices as well, because CPU and input output devices are something which are kind of, we can say, resources of the computer system, and we want to optimally use these resources. And in order to use these resources optimally, one thing is very, very sure, that a single program cannot keep either the CPU or the input output devices busy all the time. So let's say there is a single program which is executing inside the system. So at a given point of time, either it needs some CPU CPU cycles in which CPU has to attend that program, or maybe at the at another point of time it needs some input output devices. But a single program is not going to keep both of them busy at all the times, because sometimes when it is kind of interacting with input output devices, CPU is sitting idle, and when it is taking CPU cycles, your input output devices are sitting idle. So even if your single users frequently have multiple programs running, that is kind of one way of keeping the CPU busy. But is this the way through which CPU is going to be busy all the times? That we need to see. Or the another idea could be, instead of single program, can we rely on multi-program? So multi-program, when we see, that means that's basically I can say a process or a variety of operating system or a process, let's say. So multi-programming increases the CPU utilization. How? So in case of multiprogramming, jobs are organized. So when we am talking about jobs, it is consisting of code as well as consisting of data, and these are organized into memory. Now when we are talking about multiprogramming, that means there are more than one programs, there are more than one jobs, and let's say I am having a list of programs or a list of jobs. Let's say job 1, job 2, job 3, job 4, job 5. All these 5 jobs are looking towards CPU to obtain its CPU cycle. So at one point of time I can say CPU is always having at least one job to execute. So what I did, actually I switched from a single programming system to the multi-programming system, and in these types of multi-programming system, your operating system, what does it do? It keeps several jobs in the memory simultaneously. Now, and it is having multiple jobs which are waiting for CPU, and it will allocate CPU to one of the jobs. Now with this solution there comes multiple problems in the sense multiple constraints which we need to, or which operating system needs to take care. First thing is, main memory is not very large. We have seen in our last lectures about the storage structure. So our main memory is small to accommodate all the jobs. So what is to be done? So one idea is, we can keep some jobs onto the hard disk, which is our secondary storage, and this hard disk is kind of arranging a job pool, and from that particular job pool we will take some jobs and we will keep those jobs into the main memory, and that job pool consists of all the processes which are residing onto the hard disk or onto the disk, and they are awaiting the allocation of main memory. So in main memory, let's say we have a space for keeping 4 jobs, so 4 jobs can be kept there, and then another, let's say 7 jobs which are waiting for the allocation of main memory are kept in onto the disk. So this is kind of we can say how we deal with the storage in case of a multi-programming system. So if you want to have a look on the multi-programming operating system layout, so those operating systems which operate on the process of, or on the, we can say, concept of operating systems, multi-programming systems are known as operating system with multi-programming, or simply they can be called as multi-programming operating system. So here one kind of a figure is shown in which there are memory addresses right from 0 to maximum. So maximum depends on how much memory do you really have. Then we have operating system in the low area of the memory. Then we have job 1, job 2, job 3, job 4. Now why this operating system is residing into the memory, that was being kind of taught, or that was being cleared when we were kind of going through process of booting. So process of booting itself says loading of operating system from hard disk into the memory is known as booting process. So in the process of booting, your operating system is comes up here and start residing here. For the time being, your machine is switched on and it is working. Now for a particular point of time, or on a particular point of time, we have job 1, job 2, job 3 and job 4. All these jobs are residing onto the main memory, and now they are waiting for their kind of CPU allocation, or we can say some other input output allocation. So that we will talk in a short while, but this figure is showing you the layout of a multi-programming operating system. So basically that is the operating system which supports the concept of multi-programming. That means within the memory we have many jobs residing onto the memory, which are waiting for other executions or other things to be happen to them. Now which all jobs will be kept into the memory, and which all jobs will be going to we can say reside onto the disk and then wait for the memory allocation. So basically the set of jobs in the memory is going to be a subset of the jobs which are kept in the job pool. This job pool is taking place, or this job pool is being kept onto the hard disk. So whatever, let's say we have some 14 jobs, or let's say we have some 10 jobs in the job pool, and 2 or 3 will be selected. How they will be selected, that we will be covering in a short while. So let's say 2, 3, 4 jobs will be selected, and those jobs will take up into the random access memory. So basically what I am trying to say here is the set of jobs in memory can be a subset of job, or it is going to be a subset of jobs which is kept in the job pool. Now what is the duty of operating system here? The duty of operating system here is to pick one job and begins to execute that particular job, or help in the execution of that particular job which is residing into the main memory, because it cannot pick a job from the job pool residing onto the disk directly and start executing it, or start helping it to execute. No, the operating system first need to load that into the main memory. So basically the job which is going to be executed has to be present into the main memory. Now in multiprogramming system, as I have told you, that there are multiple jobs which are sitting inside the memory and waiting for their execution. So operating system is the entity, or operating system is the one who is responsible for picking the job and making it executed. Now what will happen here? Let's say for example we operating system by some mechanism, or by some priority kind of thing, it has taken job number 1, and job number 1 is getting some CPU cycles and getting executed. Now in between it may need something which is dependent on the input output devices. For example, it is a program which is waiting for an input from the user. So then in that situation it is waiting for an input output operation in order to execute it further. So what will happen this time? So by the time this job 2 is going to talk to your input device for taking the input, your CPU is sitting idle. So operating system will take another job from the main memory and start helping it in its execution, or CPU cycles will be given to that particular new job while the job 1 is talking to your input devices. But let's say so basically what is happening here is one job is being executed by CPU and another job is talking to the input devices. Now this is a situation which is only possible in case of a multi-programmed system. In case of a single programmed system, or we can say in case of a non-multi-programmed system, what happens, for the time being for which your job 2 is talking to the input devices, your CPU would sit idle, and making the CPU sit idle is not the optimal we can say utilization of resources, because CPU or the processor is a very important resource inside within a computer system, and we must try for its optimal utilization. So in case of a single program, or in case of a non-multi-programmed system, when the CPU is sitting idle, that's not considered as a good scenario for the whole of the system. Now this is actually being taken care by the multi-programmed system, in which the operating system simply switches and executes the another job, and when the previous job is waiting, another job is getting some CPU cycles and so on. So in parallel 2-3 jobs or maybe more are doing their kind of we can say execution. So one is talking to input devices, maybe another one is talking to operating devices, one is being handled by CPU. So eventually when the first job finishes waiting and gets the CPU back, so as long as the least one job needs to execute, the CPU is never idle. So let's say job 2 was talking to it, then job 2 went for an input device, so job 1 came into the picture, job 1 after certain time went for an output device, then job 4 came into the picture. So depends. So as long as there is at least one job which needs the CPU cycle, your CPU is never sitting idle, and that's what the we can say ideal situation which we are looking for here, that the CPU, which is the most important resource of your computer system, should never sit idle. And this basically happens, or this is possible in case of a multi-programmed system. So a multi-programmed system, basically we can say, is going to provide an environment in which the various CPU resources, for example your CPU processor or CPU cycles, we can say, the memory and the peripheral devices are utilized effectively. So this is a win-win situation for all. For operating system, it is keeping all the resources busy. It is keeping the memory utilized up to its optimum by keeping some 4 or 5 jobs into the memory. It is not allowing CPU to sit idle, because one after another the jobs are in the we can say a queue, and those are waiting for CPU, those are waiting to get CPU. And there are some other jobs also which are talking to the peripheral devices. So basically all these system resources in case of a multi-programmed system are going to be utilized effectively. But what is the problem here? In case of a multi-programmed system, if we see all these kind of jobs, they don't provide for user interaction with the computer system. So user interaction with the computer system means, for example, let's take one more variety of operating system, which is, I can say, time sharing, or we can say multitasking also. Both are fine here. Both are the terms which can be used simultaneously in context of an operating system. So this time sharing basically is a logical extension of multiprogramming. So when I say logical extension of multiprogramming, what does it mean? So we have seen that multiprogramming scenario in which some few jobs are there inside the memory. CPU is taking these jobs in order to execute them maybe turn wise or some priority wise, and within those some jobs are also talking to peripheral devices. So that was the typical scenario of a multi-programming system. But when we want to extend this whole system logically, we are expecting the switching, job switching for CPU. So basically in time sharing systems, the CPU execute multiple jobs by switching among them, but the switches occur so frequently that the user can interact with each program while it is running. Let's say here is a kind of, I can say, a single user system which is having multiple jobs going on its system. So let's take a very realistic example, that as a single user I have given some commands to print, let's say, some 100 pages, and that printer is busy printing those. While printer is busy, I have played some songs. So one more application is kind of running on the system, and while these songs are being played in the background, I am also typing kind of a letter or any document onto the Word. So basically, if you can see from the point of user, from the point of user's point of view, there are 3 jobs which are going on. One is being executed by printer, which is a peripheral device. Another one is an application, let's say there is a kind of document typing onto the Word, and the third one is which is playing of songs. It is also being done by the help of a peripheral device, but these three jobs are going on. So your CPU or your operating system, I can say, these multiple jobs are executed by switching among them, and the switching occurs so frequently that the user can interact with each program while it is running. So user is having kind of an idea of that document typing is going on, and that songs playing, he or she is also enjoying. So a switching is happening between all 3 jobs, and CPU is given to all 3. CPU or required peripherals are given to all these jobs. So who is going to ensure the we can say a proper switching between these jobs, it is none other than our operating system. So this is basically, I can say, a time is being shared, time of CPU is being shared between the many jobs. So this is what you call time sharing, which offers a logical extension to multi-programming. But for time sharing, we need an interactive computer system which provides direct communication between the user and the system. So, normal computer systems which we have are actually our interactive computer systems through which we can directly interact with the computer as an user. Basically, when we say an interactive computer, that means it is able to take the commands, it is able to execute those commands, and it is able to send the output to the user which is desired by the user. So that's a kind of interactive computer system is required when we talking about time sharing systems. So basically, in those time sharing systems, what is very important thing? The very important thing here is that the response time should be very, very short. For example, multiple jobs are being executed, and so all those jobs should take up CPU, or those jobs should have some response within a very, very short time, and this short time is typically less than 1 second. So for this, what does this user is going to do? The user gives instructions to the operating system, or maybe to a program, directly to use input devices, any input devices it could be keyboard, mouse, or whatever devices, and waits for immediate results on an output device. And the meanwhile, the whole CPU is the whole CPU execution and other things are being managed by operating system. So whenever we are giving some input, let's say to a kind of, we can say, C++ program or any other program for that matter, we are expecting a kind of response which is very quick, and that response I am talking about should be less than kind of a second. Now when we talk about a time shared operating system in detail, so we can say a time shared operating system is an operating system which allows many users to share the computers simultaneously. So many users are sharing the computer, and many users are giving all those commands to all those jobs to be executed to the operating system. And since each action or command in a time shared system tends to be short, only a very little CPU time is needed for each user. So even if there are kind of a let's say we have a real time system, or it's a multi user system, so and multiple users are working on that particular system, but even all those users, let's say 10 users are working on one computer system, so all those 10 users are submitting their command, or submitting their action, or submitting their program to get executed. Your CPU is actually so very fast that only a little CPU time is needed for each of these users. So it is kind of a win-win situation for CPU and the operating system both, that this CPU keeps on switching between the time so that it should not sit idle, and maximum utilization of CPU, which is a very kind of important and a rare resource of the computer system, should be done. So as the system switches rapidly from one user to the next user, each user is having the impression that the entire computer system is dedicated to his or her use, even though the system is being shared among many users. Now other users are every user is under an impression, or under, I can say, a mirage that the entire computer system is working for him or her, which is actually not the case. The system is actually kind of being shared among many users, but the users are not aware of this fact, or they may not kind of feel that fact, because the time slot in which the user is expecting a response is kind of big enough for a CPU. CPU is going to process his or her job or command in a very short while, which is less than a kind of a microsecond or maybe a nanosecond, and it is given to the user within a second. So user tends to think that the whole computer system is dedicated to his own use. So right from the starting of this lecture, we have seen that there can be kind of variety of operating systems along with its own commonalities in each and every one, and in detail we have seen the multi-programmed system, and then as a logical extension of multi-programmed system we have switched to time sharing system, and we have seen how this time sharing is actually kind of working in case of a single user and in case of some multiple users working on a single computer. So this is for all this lecture, and here is a list of references which is being used in preparation of the talk. Hope you have enjoyed the lecture. Thank you.